hopefully this will be review for you. Because I know you were supposed to have seen molecular orbital theory in the freshman year at the end of Chem 1, I think. And then I know you saw it in organic, right? Did you see pi bonds and sigma bonds and stuff like that? Okay. I always start at the beginning, though. I don't want to just assume that, like take the last lecture in organic that talked about MO theory. And I'm trying to compete up here. Okay. I don't want to take that last lecture and then just pick up right after you left off in organic. So we're going to back up a little bit and talk about the basics, and then it'll ramp up fairly quick from there. Okay, so let's talk about molecular bonding and structure. There's a couple of theories for molecular bonding. Now, local bond theory is what we've been using so far. That's how we created the structures of our molecules for point groups. This is the Lewis dot formula, valence shell electron pair repulsion theory, and hybridization. So we're really familiar with that. We've been using that all semester. Okay, trigonal planar, trigonal bipyramidal, and all those kinds of structures. That's local bond theory. Okay, and what we're talking about today is molecular orbital theory. So totally different beast. So this is what matches UV photoelectron spectroscopy and X-ray photoelectron spectroscopy, and we'll talk about that next week. And we'll today talk about simple molecular orbital theory for diatomics. And it gets pretty complicated when you get beyond a diatomic. So I remember reading, this is really funny, I remember reading my freshman chemistry textbook for some homework assignment at UT in 1987, okay, in the fall of 87. And I remember molecular orbital theory, and I'm reading the paragraph, and I didn't understand it. And I remember reading it again, I still didn't understand it. And I read it a third time, and the light went off when I realized the word molecular orbital is what we're talking about. It's an orbital that goes over the whole molecule. We've been talking about atomic orbitals, and those are the orbitals on individual atoms. And this, just think about the words that we're using. Molecular orbital, the electron cloud has now spread over the whole molecule. So 2 electrons can go over the whole molecule. They're not local. They're not stuck between 2 atoms. That's the difference between local bond theory and molecular orbital theory. Now we have an orbital that goes over the whole molecule, and it still contains only 2 electrons. So those 2 electrons are spread out over an enormous space. Okay, so that's the main point. So let's talk about all homonuclear diatomics are D infinity H. We're going to start with those, the simplest molecule, hydrogen. And so here's our D infinity H character table and those labels on the left. Remember I said they started out with Greek characters and it just got unruly. And so then we switched to A's and E's and T's and so on. So these are the A1G, A2G equivalents to the sigma plus, sigma minus, and so on. Now, whenever we have a homonuclear diatomic, let's just do hydrogen. That C infinity axis here is the Z axis. And so then the other 2 axes, X is coming out front and Y is there. Okay. So that Z-axis is the axis of the molecule for a homonuclear diatomic. So just kind of get that in your head because we're going to be using that for 2 weeks. So here's the hydrogen atom, and look at the little pictures. Whenever we shade or color those orbitals, those atomic orbitals, that's really an oscillation that we're trying to show. Okay, so they're flashing, and what we are trying to signify with the colors is an expansion or a contraction. Remember, these are the spherical harmonics, so it's harmonic motion of the electron cloud. And so when we have, look at the bottom one, they're all the same color at the same time, so they're all expanding and contracting together, and those orbitals overlap with each other quite a bit. But in the top one, the top's expanding while the bottom's contracting, and the bottom's expanding while the top's contracting. And so it's doing this, so they're really not interacting with each other. They're not overlapping. There's a node that moves up and down between the 2 nuclei. Whereas the bottom one, they're interacting and not. They're oscillating together, so there's a lot of overlap. And the overlap is the strength of the bond. So if there's lots of overlap of those atomic orbitals, there's a strong bond there. If there's no overlap, we have a node that weakens the bond. And so that's where we get the bonding and antibonding language. Now for a diatomic, there's only one bond, so it's easy to classify. It's bonding or antibonding. But you get to polyatomics, and you might have nodes on the CH bonds and a good bonding orbital for the carbons, or you might have bonding for all 4 CH bonds and a node for the carbons, say an ethene. And we'll look at that later. But it's not as easy to classify an orbital as bonding or antibonding when you get to polyatomics. But for diatomics, it's very easy. Now, in terms of energy, why is this energy lower? Well, think about it. Now that orbital, it's a molecular orbital, it goes over the whole atom, the box is increased, and whenever the box increases in size, that L is in the denominator, that size is in the denominator, so the energy drops. And then up here we have a node. So we have a big box, but we have a node, and so then that raises the energy because you have higher curvature. So we can even understand how these energies have split in the middle. So these interactions give us 2 different energies. We bring in an electron for each of the atoms. Oh, here, let's talk about this for a second too. This is a little shorthand way. So you can draw the pictures or you can write this out. Look how I'm writing this wave function. I'm just saying the 1s on atom A plus the 1s on atom B. And so whenever they both have the same sign, they're in phase with each other. Up here they have an opposite sign. So the 1s on atom A has a plus in front of it. It's omitted because we don't typically put a plus in front of our numbers if they're positive. But we have a plus 1sa minus 1sb. That means they're out of phase. That means they're different colors. Okay. So we might call this one plus and minus here. Make sense? Okay, so that's that little shorthand, and we're going to use that also through the next couple of weeks. Then each of these atoms brings in 1 electron, and then they pair up in that bottom molecular orbital. Remember, that's a molecular orbital. We've drawn 2 spheres, but really it goes over the whole molecule, and it has 2 electrons in it. This energy difference is a function of the geometry. If we pull those hydrogens apart, then this energy difference gets closer together. And if we push them together, there'll be a spot where that energy difference is the maximum. Okay. And this is what we see here in the potential energy surface for this molecule. So before we showed what we call a bound state. And we talked about an unbound PES. Yeah. And so if we could bump an electron from the bound to the unbound, then this molecule would just dissolve, okay? So it would just fly apart, okay? And then we can also label the symmetries of these. Using the character table, we could use inversion and the rotational symmetry and so on, and we could assign various Millikan notations to those, and then we could determine whether X, Y, Z, or polarized light could cause this transition. So we're going to go back and use some of our electronic spectroscopy stuff and combine it with this MO stuff. So let's look at some of the other kinds of bonds with p orbitals. So here's the sigma and sigma star bonds. Okay, so up here we have the sigma bond. So this would be the pz orbitals. PZ on atom A, say, and then the PZ on atom B. And I mean, convention-wise, I don't know. You just have to I don't know, define your terms. I would call this one, even though you know, you could write it other ways, but I would say this is PZA plus PZB, just to show that they're in phase. I would use the same sign just to show that they're interacting with each other. Someone could argue with me on that one, that since the one on B is the opposite color, that this would be a minus and the minus would be the bonding one. So you know, you could do it either way. But what we're going to say then over here, if this one is the plus, then this one over here is the minus. PZA minus PZB. And this one has a node in the middle. Although I really hate this picture. I used it out of the textbook, but it's kind of garbage because it really looks like they touch. Okay, and there really should be a node, a stronger node there. So I would draw this one like this. Here's my two nuclei, and I would draw a big old lobe on this side, and then kind of a squished one on this side, and a squished one on this side, like that. So that would be a decent picture for the sigma star. And so this one's a sigma bond, this one's a sigma star bond. It's got that node. This one has 3 nodes. There's a node on each of the nuclei. And this one only has 2 nodes. It's got a node right there and a node right there. So you know now which one's going to be higher in energy. This one is going to be up at the top, and this one is going to be down here. Right, and that should be straightforward. I mean, y'all have seen this before. We've got the PZ orbitals coming in, end on, we say. So the ends of those orbitals are coming in and interacting with each other. And then from Gaussian, if we take a molecule like nitrogen, we stick it in Gaussian, here's what that looks like. So it's this bonding, the sigma bond looks like this. One thing that sigma interactions have is they have this rotational symmetry. Notice that orbital has a, it's a C infinity axis around that orbital. It's like a donut in the middle. I mean, there are no nodes that contain the axis of the bond, only nodes that cut the axis of the bond. Contrast that with the pi orbitals, or pi bonding. Okay, this is what we call side on, so the p orbitals are interacting side on. Again, they're expanding and contracting. That's what the pluses and minuses indicate. And so even if this plus expands here like that, at some time this minus is shrinking, and this one up here is expanding while this one shrinks. And you see that really does eliminate their interaction. So they're not, it's almost kind of like they're tilting a little bit because one side is getting bigger and the other side is getting smaller. So this node may sort of wiggle a little bit, but it's still a node between those positive regions and negative regions. And so that's and then in terms of its symmetry for the D infinity H character table, it's Gerada. It's positive under inversion. So, if I go anywhere in this orbital and look at the same part of the molecule through the inversion center, I see the same sign. And so that's Gerada. So I do want to point out that Gerada and Ungerada have no bearing on whether it's bonding or antibonding. And that's a common mistake that people make. They think, oh, it's Gerada, so it's bonding. No, that's not true. Here in this case, the antibonding is Gerada. So we would call this one a pi star. And over here, we would call this one a pi. And so here again, I would use the plus 2pa and plus 2pb to show the bonding one, and the minus to show the antibonding. And here again, that nodal plane, there's the pi bond on nitrogen. So we could put all this together in nitrogen. We could show all the sigma bonds and all the pi bonds, and that's what I have here. So we've got sigma bonds, we've got pi bond number 1 in the XZ plane, and pi bond number 2 in the YZ plane. Here's a kind of a transparent picture of all the bonding orbitals in nitrogen. It's doubled up because I can't tell which one's going to be nicer on the screen. On my screen, the one on the right is really washed out and the left one looks good, but on the projector, the one on the right looks better. So you can see inside there, I guess, you see this green donut, that's the sigma bond right there. And this is the node for the sigma bond, and they're the end caps of the sigma bond. Okay, so those are the PZ orbitals interacting. And then, so if this is the Z axis, we can just draw, I'd say the Y axis here, or X, we'll call that X. And then we'll call the Y right here. So, yeah, and so then we have that pi, the px orbitals interacting, and that gives us bonds in the xz plane, and then the py orbitals acting side by side in the yz plane. Okay, so let's look at helium and why helium is an atomic gas and not a diatomic gas. right? Because hydrogen, you find hydrogen naturally as a diatomic gas because of that MO diagram. It's more stable as a pair, make those spin paired electrons, got a bigger box for your electrons, so it's lower in energy. So when two hydrogen atoms meet, they bond, and we're good, okay? Two helium atoms meet, they try to bond, and the antibonding orbital is populated as well. So they come together, the orbitals split. One orbital says, hey, I've got more space, my two electrons spread out, but the other one says, yeah, but I've got a node in the middle, and that doesn't support the bond at all. And so we have these 4 protons, 2 in each nucleus, that would really like to have 4 electrons in between them, or at least helping them be attracted. And the antibonding electrons say, no, we're not interested. We're going to stay more on the outside of the nuclei and not interact with each other. And so there's just not enough Coulombic charge between the atoms to hold that molecule together. And so they bounce off of each other. You see this instantaneous adjustment, though, into the molecular orbital diagram. They split, but the antibonding and the bonding are equal. And so the bond order is 0. And so then the atoms come apart and the electrons split back into their atomic orbitals, and then they go on their merry way. So this happens so fast, 10 to the minus 13, 10 to the minus 15 seconds, this collision. And the argon at 1 atmosphere pressure, the room temperature is colliding about 10 to the 13 collisions per second. And so they collide, they interact, they dissociate, and it all happens so fast. And remember the Born-Oppenheimer approximation, the nuclei are moving so slowly for the electrons. The electrons are 1,000th of the mass. And so we're talking about collisions of these atoms. As soon as they get close, these electrons are already making molecular orbitals and interacting with each other. It's amazing how fast things go. Okay. Now we get into the full diatomic MO diagram. So let's look at fluorine. Hopefully you can see the combination here. Down here at the bottom we have the s orbitals, and then above we have the p orbitals interacting. You have the A1G orbital, which is that sigma, and then that would be the 2s on atom A plus the 2s on atom B. Then the A1U interaction, which would be the antibonding orbital, where the 2s A and B have different signs. You see what I'm doing with this notation over here. So I'm just changing the sign of one of them. And these are called linear combinations of atomic orbitals. So I'm going to go ahead and just put an arrow there and here. Okay. And then we bring in the PZ orbitals. They come in end-on, so we're making all of the sigma bonds first. And so when they're in phase, the 2PZ on atom A is in phase with 2PZ on atom B. We'll call it a plus interaction. And then the A1U is when they're out of phase with each other. Okay. And then we have the side-on interactions. Those are E1U for the bonding. And those are, again, side-on 2px on atom A in phase with 2px on atom B, 2py, so 90 degrees to that. And then the antibonding are E1Gs, and that's the 2px out of phase with the 2px, and then the 2py out of phase with the 2py. Okay. So there's it. That's all. Now, here's the thing. How do we know how many molecular orbitals we should have? If you bring in 2 atomic orbitals, you're going to make 2 molecular orbitals. We saw that with helium. And we saw that with hydrogen, okay? If we come in with a 2s and 3p orbitals, that's 4 on each atom. And so we come in with 8 atomic orbitals, we better have 8 molecular orbitals. So the number of orbitals is conserved. So if you come in with atomic orbitals and there's 8 of them, you're going to have 8 molecular orbitals. And we see that here. We have 4 sigmas and 4 pi's. And then we come in with electrons. So the fluorine atoms, they have 7 valence electrons, right? So we've got 1, 2, 3, 4, 5, 6, 7. We're one away from a noble gas configuration. And so that comes in from both fluorine atoms, so we better have 14 electrons. The number of electrons is conserved. So we come over here, we have 2, 4, 6, 8, 10, 12, 14. So we have 14 electrons. Okay, what if we made fluorine minus? Like if this molecule, we put another electron on it, well, it would go up here, okay? What if we made F2 2 minus? Well, it would be there. And then we would have the equal number of bonding and antibonding electrons in our orbitals, and the molecule would dissociate. So that's one way to get fluorine to dissociate, is to bombard it with electrons gently and have it accept a couple of, and then you have fluorine atoms, each being -1. Okay. Same kind of thing for oxygen. So we can talk about it. The 2s orbitals are either out of phase or in phase, so they come together and they split. The 2pz orbitals can come end on, in phase or out of phase. If they're in phase, you have the sigma. Out of phase, you have the sigma star. And then the px and y orbitals can bond side and side, in phase for the pi and out of phase for the pi star. Now, for the smallest atoms, so from lithium through nitrogen, we have what we call sp mixing. Look at those molecular orbitals. This is maybe where we deviate from what you're used to in the past, okay? What do we mean by sp mixing? Well, look, these should be s orbitals down here, and they look like p orbitals. So we've mixed in a little bit of the p orbitals because the s and p in these atoms are pretty close. We don't have a lot of protons, and so we're not pulling those s orbitals close to the nucleus. And so they're up there kind of close enough in energy for a little bit of pi or p character to get in there. Now, this is nature doing what we do in Gaussian, right? What do we do in Gaussian when we say 6-31G and in parentheses we put D and P? We're mixing D orbitals into like a carbon atom. We're mixing P orbitals into a hydrogen atom. So we do this in Gaussian already. Why do we do it? To give the electron more freedom. So remember, the electrons are not mathematicians. They're not saying, gee whiz, I'm stuck in an s orbital and I really wish I had some p character here. Okay, they're going to do what they're going to do. And mixing in a little bit of the p orbital into those two s's allows us to better predict the properties of nitrogen and carbon, dicarbon and diboron and so on. So lithium through nitrogen feature sp mixing, but that's it. Okay, once we get to oxygen and above, so aluminum, silicon, phosphorus, magnesium, and so on, those there's more protons in the nuclei. They pull those s orbitals closer in, and so we really don't see sp mixing for those other elements. But for the second row elements, those first 5, we see some sp mixing. And so these are what the orbitals look like. The reason we know this happens is will be obvious here in a second. So notice the 2s orbitals aren't doing anything very surprising. They still have a lower energy and an upper energy, a lower energy bonding orbital and a higher energy antibonding orbital. But look what's happened here to the PZs. Now the PZ is above the pi bond. Okay, so this sigma bond has moved up. It was down here, and now it's up here. So that's a big difference. That's really the only difference between the sp mixing is that these orbitals have swapped places in terms of their order. Okay, but the pi and the pi star, they haven't changed at all. And the symmetries haven't changed. Okay, just their energy, their relative energies are the only things that have changed. So let's look at that. Let's look at that whole second row of diatomics. Okay, here's the MO diagrams for the second period. So notice this is just the middle parts of those diagrams. So each one of these is its own little MO diagram. Can you see that now, this little pattern? We got sigma, sigma star, pi, sigma, pi star, sigma star. And here are the symmetries, and we're going to follow that A1G level, that PZ interaction. And you see it shows up way over here. It shows up below that pi bond in fluorine. So fluorine and oxygen has that pi bond, that sigma bond below the pi. And then for lithium through nitrogen, because of sp mixing, we have that sigma level above the pi bond. And so let's introduce this idea of bond order. So we take the number of electrons in the bonding orbitals and subtract the number of electrons in the antibonding orbitals. Okay, so number of electrons. Let's see. Let me erase that for a second. Number of bonding electrons is N, and N star is number of antibonding. Can you understand ABE? Antibonding electrons, okay? My handwriting's bad enough. This is just as good. Okay, so you take that difference and divide by 2 because it takes 2 electrons to make a bond, and we call that the bond order. So, okay, what I wrote in hand is written there in text. I haven't memorized my animations, apparently. So here, these are the stars. You look at those sigma stars and pi stars, and we add up all of those, and we subtract the antibonding from the bonding, and we can calculate the bond orders. So here are the bond orders. You can check my math with your own notes, but this is a bond order of 1. Here, the bonding and antibonding equal, so it's a bond order of 0, and so on. We can go all the way down the way. One other thing to point out, too, is whenever you have unpaired electrons, remember those electrons, we call it spin, because it's a charged particle, and it displays a magnetic field. And spinning charges give magnetic fields, like an electromagnet. And so whenever you have unpaired electrons, the nucleus is what we call paramagnetic. It reacts to a magnetic field. It's drawn into a magnetic field. And so this is one of the ways that we know that these are unpaired electrons. Now, if this B2, so diboron, if that level was down here, then this would be non-paramagnetic, because those electrons would be paired up in that sigma bonding orbital. And so that was our big evidence that this sp mixing was occurring, was that B2 was not paramagnetic. And so like, wait a second, that sigma bond is above the pi bonds? How did that happen? You add in sp mixing and that fixes it. Okay, so that's one of the evidences for the sp mixing. So here's up at the top, that bond order. That's sort of the theory behind all of these different features. So this tells us that hydrogen molecule has a bond order of 1. You see this bond order of 1 here. And it tells us that helium accurately has a bond order of 0, right? Because the antibonding and the bonding electrons are equal to each other. Then dilithium, wait a second, Star Trek? What? Okay, we've got dilithium. It's not a crystal. Okay, I guess you cool it down, you could make dilithium crystals, but I wouldn't want to touch them. Okay, and so it has a bond order of 1, so dilithium is a thing. Diberyllium, though, should be a bond order of 0, and so it shouldn't exist. And then you move your way up, and you have this triple bond in nitrogen. As we're adding electrons and nuclei and so on, we get a stronger and stronger molecule, but then we keep adding electrons and it starts dropping off. The bond order drops off because we're populating those antibonding orbitals. So as we're going up to B2, C2, N2, we're adding electrons in bonding orbitals. If we go to O2, F2, Ne2, we're adding electrons into antibonding orbitals. And so then the bond gets weaker and weaker. This also tells us what happens when you have a cation or an anion. So if we take an electron from nitrogen, then we're removing an electron from a bonding orbital, and the bond gets weaker, and it has a bond order of 2.5. But you can't say that cations are always weaker, because in oxygen, if we make a cation out of oxygen, we remove an electron from an antibonding orbital, and the bond gets stronger, and we end up with a bond order of 2.5. So see, you really have to understand molecular orbital diagrams to explain this kind of behavior. So let's look at the data. Here's bond energy. And look how well it matches this theory of bond order. That's pretty cool. I mean, it's the same pattern. including the cations. And so, yeah, you make nitrogen cation and the bond energy gets smaller. You make oxygen cation, the bond energy gets stronger. So that's a pretty good good correspondence to our theory of bond order. Down here, bond length. Again, if you have a stronger bond, you'll have a closer bond, a shorter bond length. Eventually, though, you do sort of the nuclei kind of get too close to each other, and they're not going to get any closer. And that's what you're seeing here with nitrogen and oxygen. They're like, oh, that's close enough. Okay, 1 angstrom, 100 picometers. I'm not going any closer than that. But then you have this really long bond length for dilithium. Now, what's going on here? These atoms are not really bonded. Those would be called van der Waals attractions. Okay, so I say they're stuck together, they're not bonded. Okay, the electron cloud does oscillate, and that's a result of what we call instantaneous dipole moments. So if the electron cloud is oscillating around these atoms, if you were to take a snapshot and the electron cloud is oscillated this way, then there's a little bit of a positive nucleus showing on this side and a little bit negative here. If it's associated with another one of those atoms doing the same thing, you could have this instantaneous dipole-dipole interaction. And so you can get dimers, but it's not a covalent bond. You see how essentially the bond energy is zero there. So it's not exactly zero, but it's really weak. And so that's really not a covalent bond. And then down here at the bottom, vibrational force constants. So if you have a stronger bond, you're going to have a higher force constant, which also means your frequency is going to be higher. So you could scale this by the reduced mass, and you could get the vibrational frequencies. Okay. So this is all of the data that kind of feeds into to our evidence that MO theory is good and that this idea of bond order is good. The only downside to this is this really only works in terms of getting this data and corresponding to bond order. It's most clearly seen in diatomics, because it's really hard to figure out what the bond order is. If you've got a molecule like ethene, and you've got a molecular orbital that covers this whole half of the molecule out of phase with this one, is that a bonding or an antibonding? In order to calculate bond order, we need to calculate antibonding electrons and bonding electrons. There's two buckets, okay? Where do we put these two electrons? They're bonding for all four CHs, but they're antibonding for the carbon-carbon. So which bucket do I put it in, bonding or antibonding? And there's no answer to that question. We don't know. And so bond order really is most clearly defined for diatomics. And it matches the data, so it is a good concept. But once you get to bigger molecules beyond diatomics, that's why we don't talk about bond order anymore, because there's really no way to calculate it. Okay. Let's take a Kahoot to see how well we got the concepts of these types of orbitals.